Well, I will start with many thanks for inviting me for this very nice event. Of course, we will speak about cyclones, but we'll hear too much about medicanes during this week and also probably the next weeks. So I would like actually to speak about all the intense cyclones, not only the medicanes or whatever was qualified as a medicane. And for good reason, to put the medicanes into context. So there are many intense cyclones in the region, and I would like to see what kind of processes actually create the cyclones, they form the cyclones, and which kind of processes they develop these systems into catastrophic storms. And this is what we're going to see today in two parts. So there is a small introduction first. So here in the big figure, you can see the trax density for 20 winters for the Northern Hemisphere. And of course, most of the cyclones take place in the Pacific and in the North Atlantic, but also the Mediterranean is a hotspot of cyclogenesis, a small one, but still it's there. And if we zoom in the Mediterranean, we can see actually that all the cyclones tend to squeeze into the maritime areas of the basin. And if we zoom even more, actually, this is why we're here, you can see several systems of them actually form such that they attain this phenomenological resemblance to tropical cyclones. So what we know about all the intense cyclones, not only the medicanes, is that they're quite frequent pretty much in all seasons except summer. And even though they're of intensity, they have shorter times, and basically they're of smaller sizes than the cyclones we meet in the open oceans. They can still become catastrophic. And we already know that they control much of the precipitation, so they control some of the climate variability in the region and also the extremes. So there are very good reasons why we need to understand these systems. And a bit of history does say that, well, there's a community that works with cyclones. MEDEX was one of the first programs. Rom can say certainly more about this. And it's nowadays that we continue with a Med Cyclones cost action in November, but the community can continue within the future Med cost action chaired by Samira. And for those who don't, actions are basically networking tools. It's the European Union funds us actually to build a community. So it's a good thing, actually, there's a continuity in this community throughout the years. It was quite a relief yesterday. Kerry asked if we all know potential vorticity, and nobody objected. So that's quite a relief because you will hear only about potential vorticity today. So just to be in the same page, well, potential vorticity, it's just a simple equation, actually. It's the product of vorticity times the stratification of the atmosphere, so the gradient of the potential temperature. And what we need to retain is it's a conserved variable, so it acts like a tracer. So it's conserved under adiabatic conditions. And here, if you cut actually the atmosphere quite high, let's say 300 hectopascal, this is what you see. You see red colors, potential vorticity, high values meaning stratospheric air. And because it's conserved, you can see very nicely the wave activity of the atmosphere. And every now and then, what happens is that the waves break, what we've seen actually yesterday. And when it breaks, you have these filaments, these PV streamers intruding southern latitudes. And here how it looks like in the Mediterranean. You have the PV streamer intruding the Mediterranean. Whenever this happens, you trigger cyclogenesis. And you trigger cyclogenesis because PV needs to be conserved. So whenever a PV anomaly in the troposphere, like in this schematic, then this translates into cyclonic circulation. So bottom line, what's quite important is that the cyclones can be can be translated into a set of interacting PV. So I will start directly with the results. of previous studies. And the first thing we'll see is how large-scale forcing actually comes to create the Mediterranean, to start the cyclones. It's about 10 years ago we started this study. We took the 200 most intense cyclones in the Mediterranean. So these are the mature state, the location of the mature stages. There are many medicanes included here, many, 10. So what we did actually was quite naively, we made a composite average of the PV of 330 Kelvin. It's a composite average of the PV actually during the mature states of the cyclones. And here's the Mediterranean, here is the United States. And what we see is this wave breaking. Remember, this is a composite average. So here we have a ridge, we have a southern deviation of the polar jet, including the Mediterranean. And if we see the anomalies of PV, this is where we will see positive PV anomalies. So this is the PV streamer. And when it includes the Mediterranean, as we've seen before in this schematic, it's where we have the cyclones triggered. This is the dashed contours, it's sea level pressure, negative. So if we zoom in this area, what we did next was this composite, now it's centered to the cyclone centers. And the PV streamer is what you see in the black contour. So it wraps cyclonically around the cyclone center. This is during the mature stage. And the cyclones form in a baroclinic environment. The colors here depict the theta E, so the equivalent potential temperature. So this is not far from what is expected by typically in extratropical cyclones. Have a large-scale forcing, a baroclinic environment, and you trigger the cyclone. And this pretty much happens to all the 200 cases. We try to go a bit further and we try to understand what steps actually lead to this cyclone formation. And we tracked different features in the process, and we ended up with a scenario that is quite repetitive. Every time you see the same scenario for all the 200 cases. And this is a 5-step procedure, and I will start from the last step. So you have a Mediterranean cyclone. That's right, what we expect. Before that, you have the PV streamer including the Mediterranean. So we basically connected all the cyclones with these positive PV anomalies here. But there is also Rossby wave breaking. So there is a very narrow ridge somewhere close to this PV streamer. So we connected this positive PV anomaly with negative PV anomalies in the northwestern side. And we found out actually that when you have this ridge, you have always warm conveyor belt outflows that amplify the ridge. And for those who are not really accustomed with the term, here is a schematic of a typical extratropical cyclone. So you have the cold front, you have the warm front here, and the warm conveyor belt is the airstream that starts from the lower troposphere and goes slantwise over the warm front and goes up until the tropopause. This is what creates the coma shape, characteristic shape of cloud covers in extratropical cyclones. But what is also important is that they transfer low PV air from the lower troposphere towards the tropopause. And to have a warm conveyor belt, you also have a cyclone in the Atlantic. So here how it looks, this chain of events in a real case. These are very messy figures, but I'll try to here. So this is 60 hours before you get a mature cyclone in the Mediterranean. So in gray colors, you see the potential vorticity in the higher troposphere, at 300 Pascal, and it's fairly zonally. What you have basically is an extratropical cyclones. Here's the green line, and the contours, the red contours is the sea level pressure. And this cyclone moves polewards, and the magenta dots is the outflow of the warm conveyor belts when they reach the higher troposphere. And you see how they get squeezed actually here, starting forming the ridge. And 24 hours later, they start amplifying the ridge. And eventually, when the cyclone is mature in the Mediterranean, you can still see how you have this like wave breaking pattern and the PV streamer including in a tilted way the Mediterranean, and you form the cyclone where the star is. this was quite repetitive, tracking all these 5 features in the chain of events that leads to Mediterranean cyclogenesis, repetitive scenario pretty much for all the 200 cases, with huge variation because it's quite chaotic. You never have a single cyclone forming the ridge, or you don't have only warm convergence by a single cyclone amplifying the ridge. So it's not quite obvious what happens here. So what we did with Alex Sherman here is we tried to simplify this chain of events, and we took the Worf model. So it's a regional model. Here is the domain we have. And we forced the model with constant boundary conditions. And the initial conditions were the same. And it's the climatological average of winter atmospheric state. So there's no wave activity, it's just a very smooth average. And what you see here in colors is PV at 300 hectopascal. And what we did, we planted a bomb here. We planted huge PV anomaly just to trigger a cyclone. So 0 days, it means that initial conditions were like this. So we trigger the cyclone, and 2 days after, you can see it gets strong, and how it forms actually this narrow ridge-like structure. And you can see the PV streamers start forming over the Atlantic. And you can see 4 days later, including the Mediterranean, and here it starts the cyclone. So we simplified the picture, and we could provide some evidence at least, but this is how we expect things to happen just before the cyclone starts in the Mediterranean. And of course, there are huge, huge implications into the forecast. And this is a nice study by Portman. Fanti contributed this one. And this is Zorbas. We've seen Zorbas yesterday. And still we have a cyclone over the Atlantic, and you can see how we have a ridge getting built, and eventually we have a PV streamer including the Mediterranean. So I think it was like 2 days lead time, or maybe more. But what Portman did, they took the 50 ensemble members, PCMWF ensemble prediction system, and they clustered the PV streamer into 3 different locations. So in some members, it was west than normal. In several of them, it was where it was supposed to be. And in some of them, it was east to where it was supposed to be. And depending on where the streamer actually landed in the Mediterranean, you had different locations of the cyclone formation. So in order to get the cyclone right, in the right location, you should have the streamer also, including the Mediterranean, also in the right location. So this actually was quite important in order to get a very good prediction of whereabouts of the cyclogenesis when the cyclone will start. And that was a medicane. And what I want to say is, yeah, this is the summary of the first part. And what we've seen actually is that PV streamers are very important, actually, just trigger the cyclone. And this is all about large-scale forcing. And just to repeat the systematic scenarios, you get Atlantic cyclones. They have their warm conveyor belts, they amplify the ridge, so you have Rossby wave breaking, you have PV streamer intrusions in the Mediterranean, and eventually you get the cyclogenesis. This was pretty much discussed also yesterday about tropical cyclone moving forwards, and this has an impact downstream in the Mediterranean. But here, just to insist actually in this scenario and why it is important, the Museo actually, they studied 8 medicanes and their predictability in the Mediterranean. And what we did is for different lead times, the lead times actually is in days what you see in the x-axis. So every chart is for one medicane. They found the probability in the ensemble prediction members of this NF to have a cyclone. So if the bar is filled, it means that all members could see that there is a cyclone in the Mediterranean, regardless if it's in the right location or not. And what is quite striking is that, for instance, in this case, about 5 days in lead time, not all of the members could agree. Actually, less than half the members could see that cyclone. And suddenly, all of them could see the cyclone 5 days after. This same thing is quite striking in this example here. Suddenly, there's a jump in the signal. All of them can see the cyclone. Of course, there are success stories, there are huge failures, but pretty much we always see this jump, and this was also the case in Daniel. And what we speculate is that if you go backwards in this chain of events, if you prescribe nicely in the initial conditions of the model, the Rossby wave breaking, for instance, or the Atlantic cyclone in a very correct way, and the model can resolve it, then you have a success story. But pretty much intuitively, I could say that the predictability from cyclones is limited to 4 or 5 days. And probably because we miss something in this chain, in reproducing something nicely in this chain of events. So what we know what happens, but we how much variability we get in this one, because it's never simply and then you have downstream cyclogenesis. So there are many diabatic processes from the Atlantic cyclone involved in this process. So we need to understand better which one needs to be better represented in the models. And something that goes to future scenarios, what we have quite done recently, Marco has a nice paper on this one, is that we take a semi-5 or semi-6 model, we downscale it, and for the future, and we have a about how the cyclone will evolve. But there is nothing now, or pretty much nothing actually, about how we connect the future evolution of the cyclones in the Mediterranean with whether the semi-5 or 6 models we downscale basically correctly the wave breakings of the wave activity. So in order to be quite sure of what happens in the future in the Mediterranean, you should be sure also you have to say something also about how it will be the jet in these future projections. So up to now, we've seen actually large-scale forcing. And of course, this is not the whole story. Because large-scale forcing can tell us something about the creation of a cyclone, but if we need to see how the cyclones develop, we say something also about processes that take place within the cyclone. And of course, PV is conserved. This is what we've seen with the PV streamer, but also it can be created or destroyed by diabatic processes or by frictional forces. So up to now, we've seen actually the green PV anomaly here that creates cyclonic circulation. But also, if you have latent heat release, you create another PV anomaly that creates an additional cyclonic circulation. And basically, the cyclone is the sum of these two cyclonic circulations. This is what we get with the model. And to understand a bit better the origin of PV, what we did was with Shugray and Francesca Teugler, we basically implemented a tooling Worf model that gives us the budget of PV, decomposes PV to a conserved part. So this is whatever comes from the boundary conditions, basically, and from the initial conditions, what is purely transferred in the model. And also we get the PV that is created or destroyed by the parametrization. So by diabatic forcing, this is microphysics, cumulus scheme, temperature diffusion, and radiation. And whatever is created or destroyed by momentum forcing that comes from the boundary layer scheme. So here you get the PV profile in the center of the cyclone, of the 100 cyclones. Every gray line is one cyclone, and the average is the black line. And you can basically describe the cyclone with two main PV anomalies. You can see the stratospheric air, here a big PV anomaly, and a modest one, which basically has its maximum at around 8 picopascal. And if we take only the conserved part, so what is basically transferred, then you lose the local maximum in the lower troposphere, and we get only the PV anomaly in the upper troposphere. But if you quantify, well, you take only what is created or destroyed diabatic processes, this is what you get actually. You get the local minimum here in the lower troposphere, and you lose completely the substrate there. So there are two different anomalies that will create a cyclone. One upstairs, so this is the PV streamer or the cutoff flow, and one downstairs, this diabatic process. We decomposed more actually the diabatic processes, and of course it's latent heat that does most of the work, but it tends to be balanced actually by what you destroy from PV, from boundary layer, temperature diffusion and radiation. And frictional forces, the average is about 0, so they don't really contribute. But what we need to pay attention is an average from negative, many negative actually, PV, so you have much of PV destruction in several cases, but also you have PV production. Some cases, and we'll come back to this. So what we did actually next was to invert these two anomalies, the conserved part of PV and the non-conserved part of PV. And here you get a scatter plot. Every dot is a cyclone during the mature stage, so when it's maximum intensity. And what you see in the x-axis is the relative vorticity due to the conserved PV, so the stratospheric data. And what you get in the y-axis is relative vorticity because of diabatic forcing. And the first result is that there is something like an here, which means that the stronger the diabatic forcing, the weaker the baroclinic forcing. There are good assumptions why this happens, but it can be also due to we have only 100 cyclones, and maybe it's just an illusion because you get very small, very few points here. But the other result we got is that in red circles you get the cases of medicanes, and they don't seem to be really different from the others. Well, we thought that this is quite normal. Here, Zhang et al. Actually, they found all the medicanes. Well, they made a climatology of medicanes based on cyclone phase space diagrams. They just found cyclones that are warm core and axisymmetric. In black contour, you see this seems like a PV cutoff, which we've seen yesterday. So this fits well with what we've seen yesterday. But they also develop in a very baroclinic environment. So this is the theta actually in color. So it's quite similar to what we've seen before. And just a few case studies just to have an understanding of what happens with this scatter plot. So you have two columns actually of figures, so it's two case studies. And the upper row, you can see in color the relative vorticity in color, and the contours show the potential at 850 per Pascal, all of this. And in the middle row, you see the PV in the upper troposphere, this is the color, so you can see clearly the PV streamer in these two case studies. And in black contour, you can see the geopotential anomaly is imposed only by this conserved part of the PV at 850 per Pascal. And you can see, well, cyclonic circulation imposed is basically collocated with the cyclone centers. So there is a bit of, there is some contribution, baroclinic force these cyclones. And here we just, you see, you get the same thing, but here PV is basically the diabatic, so what per PV is produced by diabatic processes. And also you get anomalies that collocate with the cyclone center. And we're in this part of the scatter plot, of course. Both ingredients, so there's baroclinic force and diabatic forcing, they work to reinforce the cyclones. But of course, this is not the only way we get strong cyclones. So for these two cases, this is tricksy. This is one of the famous medicanes here. So there was not very conclusive signal what happens in the upper troposphere, how actually the upper troposphere forces our cyclones, but it's pretty clear what happened to the lower troposphere. So diabatic forcing basically is to be blamed for the reinforcement of the cyclones. And here, of course, we're in this part of the scatter plot. Another example of that is not super uncommon is the cyclones that form close to the Alps, actually, in this part of the region. And of course, you have always a PV streamer. You have this, they pose cyclonic circulation, of course, but you can see also the Alps, how they create actually PV. This is due to, this comes from frictional force, basically. Well, at least the momentum forcing to the model. And you can see actually it also creates a large cyclonic circulation that's expected to help the cyclone develop. And we focused in one of these cases. And what Alex did here was to use Lagrangian model, and he quantified along the trajectories, the air parcel trajectories, where you get positive and negative PV anomalies. And here, most of the positive PV anomalies come actually that end up to the cyclone center. They come from where you have the left side of the Alps. Finish actually with two cases. Well, these are the freak cases, my favorite ones. In this case, you can see actually the relative vorticity has this elongated shape. And of course, this is a smooth figure. If you go directly to the model outputs of vision, you can see the sea level pressure, how actually it outlines the cyclone, but relative vorticity, which is in color, you can see there are two local maxima, whose one representative center, and we chose the upper one because it's stronger, but both of them you have to have one center. And when we inverted actually the upper tropospheric PV, well, we had the same picture. We know actually you have imposed cyclonic circulation around the cyclone center. So there you could say this is a baroclinically driven cyclone. But when we inverted actually the abatic PV, well, we managed to outline the secondary center of the cyclone because the cyclone center we chose was here. So depending on what we chose as cyclone center would characterize differently the cyclones baroclinically driven or diabatically driven, assuming, of course, that here we see one cyclone by sea level pressure field and not two small cyclones. But at least what we see in many extratropical cyclones, you have multiple centers. So it could be also that they're multi-center for completely different. And the other freak case is this cyclone here. And when we inverted the PV in the upper troposphere, well, this is a local high, so it was super inconclusive anyway. But then we inverted what is produced by non-conserved, the non-conserved PV. And of course, it's quite clear that you have the cyclone due to diabatic forcing or whatever, or frictional forces. But actually, most of this, more than 80% of the values here is due to frictional forces. And if you recall this vertical profile, this cyclone is one of the outliers here, that you have strong production of PV due to frictional forces. And this was quite puzzling. I never seen this. So we think into this, and basically it seems that the way actually the fronts get aligned or configured to the acceleration field with the frictional forces, well, they can produce PV. And these black colors is where you have the PV production. And if it gets close to the center or they get transferred to the cyclone center, you end up to something like this. And this was a strong cyclone, it was not a negligible feature. And I thought I was turning crazy. And it was quite a relief that in another study that Attinger and colleagues did, they quantified also PV into the cyclone centers. using different methods. And so what you have in red and orange tracks is basically the cyclones that where the PV anomalies in the center of the cyclone is mostly due to condensation, well, due to convection basically. But the green tracks, and that's about 10% or less, are the cyclones where the anomalies were stronger and they were produced by the momentum forcing that comes from the turbulent steam. And that's basically frictional forces. Most of them are above the land. Some of them are above the sea, like here. To be rare, but it is there. They managed to find similar cases in different contexts completely and different methods. So I end. Just summarize that. Well, we know that the abundant, of course, they're important. Actually, they help the science develop. Mountains also are quite important. We not see the Mediterranean as something completely relevant to its geography. And it's quite possible that the basic baroclinic forcing, most of the times, there's a question mark here, of course, they're always present to the development of medicanes. We don't know, these things is where we have much of light, or at least some hints of what is happening. There are an endless list of things we don't know. I just want to highlight these fancy features we don't know. This is a medicane, for instance, in 2005. This was shown yesterday by Kay. And there's much of dust that comes into the cyclone. And we ran the model actually without, well, normal run of the model. This is a black line, shows the evolution of the sea level pressure of the cyclone. And when we run the model with direct effects of the dust, it means you allow the model, well, the dust to absorb radiation. There was a secondary maximum, well, which came well after the maximum intensity we had in the run without the dust included. Because this is the time that there was not much of convection, so the dust didn't wash out actually. And the Mediterranean is quite close to the major dust sources of the planet, so the Sahara Desert. So there is a question what happens here. And also another example is stink jets. Here is the Black Sea, and there is a case study that they noticed actually stink jets. It means that there is a very sharp, very fine scale, sharp descending airstream behind the cold front that creates very strong windstorms. This was the case, for instance, in the 1987 cyclone that hit the UK. But you need high resolution models to find the cyclone, these stink jets. And therefore, it's something we need to understand better in the Mediterranean. And there is not much up to now for this one. So many thanks.
Thank you. So we have time for questions. So, and I would encourage the young people to ask questions as well. There are no naive questions. The way it works is I'll give the cube. Is that the way it works? I give the cubes, which is a microphone. And I'll start with a silly question because I'm chairing the session. So the question is, you showed this anti-correlation between the PV forcing by adiabatic effect and diabatic forcing. Right? And in some cases, for the strongest adiabatic forcing, the diabatic one can be negative, right? So it looks like it's acting as a sort of friction. So can you explain how the diabatic forcing can be negative?
Yeah, the adiabatic forcing is quite one of the weaknesses of this method because you need to define anomalies to invert the adiabatic forcing. And the anomalies are defined by, we take a 5 days average and we just take the anomalies with respect to this 5 days average. So you assume that in 5 days, you can actually, it's enough to define the anomalies when the cyclone is during the mature stage. If in some cases you have, let's say, a persistent 5 days PV streamer or PV cutoff, then you don't. So this is, it might be a mistake in the sense that we didn't manage to capture well the PV anomaly. It can be also the case that, like here, well, this is an anticyclone base, and the cyclone is here. So it could be just the fact that the PV streamer was pretty much nowhere, and it made this negative anomaly, and this somehow created this anticyclone that didn't contribute much.
So it's more difficulties in defining the anomalies.
I think it's quite difficult.
And probably for these cases, this cyclone behave like adiabatic cyclones. That's what you would guess?
We have much more uncertainty to define the adiabatic, the anomalies, than the adiabatic one. There is some uncertainty. Yeah.
Okay, thank you.
Okay. And the question is related to the same diagram. So if I remember well, this refers to the mature stage, right? Did you see some different in the pathways between, for example, medicanes or some particular cases and extratropical cyclone? So
pathways, you mean from
the evolution and the?
We didn't do that. We don't know.
It would be interesting, I think, to analyze if there are some different evolution possible.
What we've seen in your study in 2013 was like when the cyclone is formed, you have also huge of convection, right? So they should start like both forcing should be strong at this point. If I have to assume something.
Yeah, I want to go back to that same diagram of the partition between the conservative and diabatic contributions to PV. If you take away the cases that are classified as medicanes and just look at the rest, is there a correlation with just the absolute temperature? In other words, I would guess that in the coldest part of the year, there'd be less diabatic heating, and the warmest, there would be more. It might be something interesting to try.
Yeah, true. In some cases, you get convection, you get higher SST, it might be fewer convection. In some other cases, what we've seen is also large-scale ascent. You have the PV streamer, and next to the PV streamer, you have large-scale ascent, and this also might enhance convection. I think there is also a difficulty just to say which cases are because of local, let's call it convection, in which cases you have forced convection by large-scale ascent.
My question is related to Marcello's one about the pathways. Closer? Oh. Sorry, yes. Okay, well, you say that diabatic PV is produced close to the surface, okay? But convection destroys the upper level PV, the conserved PV, right? How can we limit those cases that, well, the upper level PV is the origin of this cyclone, let's say. But some cyclones, like medicanes, continue to exist after the destruction of the upper level PV streamer, right? How can you limit this group of cyclones related to the pathway, like the evolution of this interaction between two PV anomalies, the upper levels and low levels?
Yeah, I didn't get the question actually.
Okay, let's say we have a cyclone, Mediterranean cyclone, that is due to a PV streamer coming down, introduced into the Mediterranean. you have convection close to the center that destroys this PV anomaly aloft,
Yeah.
but the cyclone keeps intensifying.
Well, in this case, well, first of all, yeah, when you have convection, you expect PV production in the troposphere, PV destruction upstairs. But PV destruction, this PV anomaly is always far smaller in amplitude than the PV streamer as such.
Yeah.
So the erosion of the PV of the stratospheric shouldn't be too strong. What I would be mostly concerned is that you have outflow due to strong convection that might chase away this absorbance case.
Yes, upper level divergence.
When this happens, actually, it means that probably the convection is too strong to sustain the cyclone itself. I don't know if there you can call this tropical transition, that there's the but that sustains the cyclone alone. Can intensify the cyclone just due to what happens to the convection from PV perspective.
Yes, a question still related to the contributions to the PV in the lower levels. Yeah, sure. Yeah. Yeah, so the question is related to the
You can have both.
okay. Reinforced. No, better. Yeah. The question is related to the PV contributions still. So maybe the answer is still that there are limitations in your way of defining this. But I saw that the boundary layer processes were always contributing negatively, or in great part contributing negatively. Is there a physical reason for that? And what is it?
Temperature diffusion.
Okay. Simple.
Yeah, I mean, it's PV is dependent on the gradient of temperature, basically. So if you have more temperature in the lower troposphere because of diffusion, and this decreases with height, then you have a negative gradient. That means negative heat.
Mm.
I will try to speak aloud without the microphone. Manos, probably you say something during the presentation, but sorry. Okay. It's okay. Okay. Probably, Manos, you say something during the presentation, but I lost this point. Do you expect that using convection permitting resolution in climate model can improve the modeling of this phenomena instead of using the parametrization as we use in climate projection?
Yeah, well, what we see here is very model dependent.
Yeah.
So, yeah, if convection permitting simulations lead to stronger convection or stronger diabatic effects, then
yeah,
the scatter plot will change, of course.
Yeah.
To say suddenly disappear and will be all of them diabatically, of course, but it will change, yeah.
In the case of dust, what might interest you is that we did a study of a Sahel of the effect of dust. And what it does is that it reorganizes the transport of relative humidity from the Atlantic Ocean over the Sahel. And it's quite strong because the absorption is enormous. So we have diagnostics where we can play the dust event and unplug the dust event and make the difference and see how the transport of relative humidity is affected over a certain area of interest. And that may be something you can also play in your simulations.
Yeah, true.
So we have a few questions online.
Only one? So
Okay. So you have a question from Marco Cerconi. who says, thanks Manos for the really interesting talk. Regarding the scatter plots of conserved PV and non-conserved PV, there is a negative linear relation. So it seems that if you have stronger baroclinic forcing, you have weaker diabatic forcings, which are the physical mechanism. So the question is, which are the physical mechanism behind that? Could be related to a seasonality of the cyclones. For instance, the cyclone with stronger baroclinic forcing are in winter, and they probably could have weaker diabatic forcings respect to cyclones in autumn, where we have the opposite.
Yeah, well, as I said, actually, we only have 100 cases here. So I'm not very, I cannot say with certitude that this negative relationship is, it's true, because we need much more points actually to prove this. But if it's true, I can have two assumptions, and I think they're not so much related. We get the strongest cyclones here, so regardless of the city. So, of course, there is a seasonality in these ones. Most of them are, that's true. But if I have to bet something, is what Stavros said, well, you have strong convection, you erode actually the PV streamer, so you expect its forcing to be smaller, but also if you have strong convection, you might somehow disperse the PV streamer because of the convection. So that could explain this negative relationship, but this is speculation, so it's what I would bet actually. But no, I don't have a very clear answer about this.
Thank you. In one of the early slides, you had the top 200 cyclones on a map. It wasn't clear whether it was the genesis point there.
No, it's a mature stage.
Mature stage, okay. So one of the things I was wondering about is you mentioned the role of mountains in terms of friction. You didn't say anything about Lee cyclogenesis, whether or not, because one of the regions there is a known region for Lee cyclogenesis. The other thing I noticed is, at least to the south of the Pyrenees, you have some sort of a big track that looks like it's going through an orographic gap, which sort of reminds me of what happens to tropical cyclones in the East Pacific. We have important orography gaps. Do you want to say anything about that?
About where's the gap here? You mean?
To the south of the Pyrenees.
Ah,
yeah. You see that line? Yeah. That line. It looks like it's going through an orography gap.
Yeah, yeah.
And then there is that other region just to the southeast of the Massif Central, which is an important Lee cyclogenesis region. So I was wondering about these other orographic effects.
Well, here I have only the mature stage, so we don't know where the cyclone started from. Okay. Some of them might came from the Atlantic.
Yeah. But could they? Yes, but could they reinforce once they?
If they could, yeah. It's what we've seen before, actually. Close to the mountains, if the flow is organized in a way that basically you have PV production.
But you attributed that to the frictional effects of.
From the model perspective, yes.
Okay.
Yeah, can you take the microphone, please? And we'll have one last question.
At this point, I would like to add the comment that I will show tomorrow in the talk, that we saw that for cyclones forming in the Western Mediterranean, there can be a favorable preconditioning to outflow from, for example, Mistral or Tramontane wind that favor the transport of intensity of surface fluxes already before the development of the cyclone. So probably that point can be related, I think, to this part.
We'll have
one last and very short question from David.
Thanks, Manos. And I was thinking also that perhaps going back to the talk by Kerry yesterday, and this Dubai floods was an event also where with the characteristics that were kind of similar to what we see in the Mediterranean. So there is a cut-off flow, and then there is a lot of entrainment of dust from the desert. So do you think we can extend a bit the Mediterranean and also, because I think there are not many teams that work on these area also of the Gulf of Arabia?
No, not yeah, not many, but I can connect it to work on the flood event in this place because they actually cooperate with the Saudi Arabian Weather Service. So
Yeah, it's the kind of phenomena that we see also in the Mediterranean, no?
similar. I
Similar.
didn't really check
Look
what
at
happened in
this. Yeah,
Saudi
that could
Arabia.
be interesting perhaps to have a look in Tropicana. Thanks.
But as far as I know, what is interesting there is few millimeters can cause a flood. So no, few millimeters. I mean, yeah, for this case, I don't know, but
Data that we have in climate meter is like over 350 millimeters
okay, that's a
over
lot.
all the Dubai metropolitan area. So it's quite a lot for the.
Okay, so maybe we can thank our speaker again.
Thank you.
We'll stop here. So as you've seen for the speaker of the rest of this week, the idea is that you connect to Slack and then connect to Zoom via Slack, and then share your screen, and it will directly be projected on the screen. Okay, so that's an illustration of why Slack is important for you to get accustomed to. So we'll break for half an hour and come back at 11:30. And remember to take for coffee. Yeah, there is coffee served in the cathedral, I suppose. And remember to take the lunch tickets for today. But yeah, and to subscribe for the restaurant before Thursday noon. Thank you.
I think it's on the media, right? Even before happening, a medicane is mentioned in the news. It's a very fancy word. Mediterranean hurricane in your country or city, it's coming. Be careful, take care. But then we need to dig into the data and find out what this cyclone was, what was all this fuss about. It's not always the case that we are talking about a medicane. This statement comes from my thesis a few years ago, École Polytechnique. After studying a few cases with observations and numerical simulations, I ended up in this short, let's say, definition, but not good. Like a medicane is an intense mesoscale maritime secluded cyclone which experienced tropospheric heating by convective activity. That's in Emmanouil's presentation. It has a frontless structure with gale force winds very close to the center. After all, it's a warm cone cyclone. The synergy of baroclinic instability and diabatic processes contributes to the formation and dissipation of a medicane, more or less what Emmanouil showed us yesterday. According to their relative contribution, these cyclones can be classified into two main categories. Those with a shallow warm core formation, driven by baroclinicity and weak diabatic processes, and those who have a deep warm core, mostly driven by strong diabatic processes, but always baroclinicity is there. We are not in the tropics, so something is not very straightforward like the cyclones or hurricanes. About 40 years ago, or 50 years ago, we didn't have the tools we have today. In order to find medicanes and, well, cyclones that have hurricane-like structures, we were dependent on satellite images. These are two satellite images, successive days, 1982, where when we had a polar low formation north of Norway and a medicane at the same time in the Ionian Sea. So you see that the medicane seems like very hurricane-like, and this is polar low, very typical polar low, and the yellow part of image. Both cyclones did not cause any damage, any known damage.
like the ones we heard recently in the Mediterranean. Now that we have tools like mesoscale modeling, we see structures very similar to hurricanes. For example, in this simulation with WRF, I used Data5 as forcing input. This is a radial azimuth average of tangentials with some tangential winds and the maximum radial winds. So you see the strong inflow towards the center of the site. W, the strong objects close to the center of the Zorba cyclone, and then the outflow above 300 Pascal divergence a lot. It looks like hurricane, like it's brief in the simulation, but maybe in the, as we saw before, kicking Greece. And we don't have all the tools that our colleagues in the US have, like the research aircrafts that fly inside hurricanes and have in situ data. But we have the opportunity in Corsica's campaign, Exciter campaign in 2018, we have this Falcon 20 research aircraft from Sapphire team. For a month, we were flying inside storms, taking microphysics into account with an LMA lightning map array, mapping the 3D structure of lightning and so on. In my second year of PhD studies, I was very excited, and we had a very intense decay in the forecast near the end of this campaign. So I was very excited that we will have, for the first time, to fly inside a medicane. So this is the forecast, like the 33-hour time step of Bolam, but most of the models were showing it. And our own model was showing a category 2 hurricane, stronger than Janus. So we didn't have a chance to prepare ourselves for that case because the FIR of Rome forbidden us to fly. All the commercial flights, all the cargo flights and research aircraft had to be down, grounded for the next 48 hours because of the medical information in the models, right? So we took the day off. We went to the beach. I took this photo this day where the forecast was showing a medicane. It was sunny, but nothing. So it was a bust forecast. Anyway, I was disappointed. The only guy who was not disappointed was the pilot, I think. He didn't have to inside a hurricane. A few years later, Medicane Janus happened in 2020. This is a graph with WRF simulations again, but using a more sophisticated model, the newest IFS cycle that will run in the future at 4.4 kilometers. Right now, IFS is 9 kilometers. So this is not released yet. We forced the model, WRF model, with this data from the side project of Nation Earth, so that the low resolution stations were better in terms of trajectory and intensity than the high resolution. Yes, the new IFS forcing makes the simulations worse for some reason. So we are trying to investigate that. So we have lots of things to learn about, maybe parameterizations in convection, maybe something else. I don't know. We will find it out eventually in a few years. We all know what a medicane is. If we need a classification of them. Sometimes, like in December 20, we see medicane, well, cyclones that exhibit subtropical or tropical-like characteristics, like this one near between Cyprus and Syria, that Met Office decided to say that it was a tropical cyclone and have to track it. After all, it's Cyprus, so it has to track it. And you see that loop of the satellite with convection close to the center of the cyclone, and there was a radar image over there showing a close circulation. After all, ASCAT measurements and stations over there reported very weak winds, nothing close to tropical cyclone. but it was nice to see from space. But was it a medicane? You tell me. Some other times have what I call pocket medicanes. They are really small. They form in the periphery of very large cyclonic system, cut-off load, in short wave troughs, vorticity maxima, but they have plenty convection close to the surface, and they have an eye for a short period of time, but they have an eye. It was like the medicane 2006 that caused severe damage in Puglia, in Italy. It was Ilona in 2015. There is a paper from Chudo Kyomi. This is the case, the latest case that I know of in January 2023. This cyclone, this diagram of sea level pressure was from the airport of in Ancona. So you see the southward drop of sea level pressure, very hurricane-like structure, and we don't see that in our Mediterranean cyclone. Also, it caused very high waves in the port of Ancona, very close to the coast. We had up to 4 meters waves. It was very high for this part of Mediterranean, because Adriatic Sea is quite shallow over there. Marco, you can correct me if I'm wrong, but it was an exceptional event in terms of waves close to the coast. So it was an important event, but local. The medicane, we don't know. During my thesis, I tried to use different tools to detect convection contributes to the dissipation of these cyclones. So in this case, we used 9 cases that were pre-characterized as medicanes. We used the satellite images to map the distribution of convection, but also we used ERA5 reanalysis to make a correlation with the deep shear, the wind shear in the troposphere. And we found some interesting results resembling tropical cyclones, that the most tense cases, like Rolf or Zorb, had lots of upshear convection during their intensification periods, where we usually expect subsidence. So distribution of convection has something to do with their intensification, not just being there and creating the abatic PV, we discussed in Manu's presentation. So we don't have, again, we don't have other data to work with other than satellites most of the time. So we also use in satellite to detect force, like we do in tropical cyclones. For this case, the Italian colleagues, this study was led by Giulia Vanagel and Pier Daderio. We used AMSU-A and NS brightness temperature to detect the warm core formation in medicanes. Found out that in not all cases, warm core was very deep in the troposphere. We had 3 channels to work with after all, meaning that they had different peak heights, their frequencies. So we can have at 400 to Pascal more or less the lowest information that we can get from upwelling microwave data. And we could classify, say, the ones that had deep warm cores and shallow cores. It was applied, this method was applied together with the deep storm database, which is a database using data to map convection in the globe, the whole world. And we took 2 acclaimed medicanes, Helios and Juliet. We found out in the media again that they were classified as medicanes. And we checked the data, it was okay. They had an eye for some periods, and we found out that Helios did not have deep convection close to the surface, close to the center of the cyclone. But shallow cumulus clouds or other type of clouds determined by the cloud top height deep storm database and ice water path, we saw that Juliet had deep convection and indeed preceded the maximum intensity of the cyclone. So Helios was not mentioned as medicane at all, and Juliet was close to the other cases we had in the past. And due to the fact that we don't have conventional detection systems for medicanes and cyclones in general, we're using some non-conventional ones, like the microbarometers that detect the nuclear tests around the globe. We were using data from the IS station in Tunisia, but due to very bad stratospheric wave propagation during most of the events, we had only 3 cases to work with. One of them was Janos, and we were able to detect both the lightning during deep convection close to the center of the cyclone, and some events related to swell, storm surge during intensification periods of Mediterraneanos that were very much collocated, like data and numerical reanalysis. I encourage you to study also this interesting presentation of Konstantinos Listovsky from SEA. Medicane case, so 2021, which was Medicane Apollo, that we'd like to discuss with you. You see that it formed close to about €250 million damage, killed 7 people in southern Italy and Malta, and was able to cruise the half of Mediterranean, reaching Turkey, causing more damage over there. Yes, there are many cyclones that do excessive damage, and they are not warm core structured. But medicanes have started, I think they have started the last 15 years to be more intense than in the past. We see Medicane Janos, Medicane Apollo, Medicane Daniel. We see a intensification, let's say, that has to be attributed somehow to changes we see in the climate. But I would also like to point out that here, this is the channel from Meteosat, right? So the peaking frequency is close to the tropopause, 300 Pascal more or less. You see that there wasn't any PV streamer before the formation of Medicane, of the cyclone, but more than 2 PV streamers interacted with the cyclone. One of them with air intrusion that resulted in the eye formation. So we have eye formation from dry air that intrudes the center of the cyclone. We don't have subsidence due to convection like in hurricanes that does the eye formation. And we didn't discuss that yesterday. It's an exception. It's not always the case. Like in Medicane Zorbas, we saw a similar thing, but also convection there had some influence in eye formation before shore. Then you see that the cyclone still exists over here, but strong wind shear creates this asymmetry. This blob of convection here survives almost 2 days before reaching Turkey. And then also a graphic effect with another round of big convection. So there are many things that play a role during the Medicane formation. I wouldn't say that we're talking purely for the tropical cyclone here. They don't have the space, more or less, to develop full tropical characteristics. And they are always pushed by other cyclonic systems, other features that were not found in the tropics. Well, this was all from me. I close with this in 2017.
Thank you. Questions?
Thank you, Stavros. Very nice talk. About Apollo, that we also tried to attribute, it was one of the first that we tried to attribute, and we couldn't with the analogs methodology. Basically, what we say was like that we didn't have enough analogs for this. And in fact, the question for you is, for this kind of event, you see, if you can go back perhaps to your satellite animation, you see that there is a lot going on before we even see the cyclonic structure, all this prefrontal thunderstorm. And if we really talk about the damages, there was when the cyclone forms, the core is there, but then there is a V-shaped thunderstorm that hit the city of Catania at a certain point, and it's persistent there for quite a while. And the hazard in Catania were mostly before the medican phase. So yes, I basically agree with you. With like there is much more than just the medican phase for this Apollo. But then the question is like, when we have this kind of events, when do we start to track them and to define them, since the impacts can also be before? So we are waiting for the medicans, but we have already Catania flooded.
Yeah.
And yeah, so.
Well, from my point of view, we need to the bottom-up development of such cycling, because we discussed about the cyclone formation, Emmanouil's case, Emmanouil's presentation, but there are some exceptions in Apollo that have bottom-up development, and this we have to prove it somehow. The best thing we can try now is numerical modeling, and we have to rely on reanalysis. Now, soon we will have R6 data, higher resolution, better physics, new insights. I would search for bottom-up development in the Mediterranean. Thank you.
Nice, Stavros. Very nice summary of this problematic. I wanted to ask you, because you showed nicely showed that it's possible from remote sensing, no, and satellite images to infer, to discern between if an eye is formed. Well, this is a question. So could you differentiate if an eye is formed from dry, from remote sensing, from dry intrusions, or from subsidence from convection? Because I will say that if the eye is formed by dry intrusion, this is what the community calls an eel-like feature, no? And we can see that in subtropical cyclones, even there have been some cases in the South Atlantic where subtropical cyclones at the major phase, they also there is an eel-like feature, but it's not due to convection, no, it's due to and when it is like sorbas yes, at the major phase of sorbas is due to convection, no, I will call that an eye, no, an eye like in tropical cyclone. Yeah. So there is a possibility to infer which is so that why the eye is forming, and because of what, just from remote sensing.
If we are lucky enough to have overpasses of some specific radiometers in polar orbiting satellites, like we did in Mianos. We have a BAMS paper about Mianos that we show that I was able to detect deep convection close to the center, and there was a hurricane-like structure over there. The subsidence, maybe, I don't know, subsidence I cannot infer from this kind of data, but we don't have, because the medicanes happen very rarely and they are very small. We need this high resolution observational data set to collocate with the eye formation and say more. Like in Rolf, I didn't have that. I had only Metasat and MHS overpasses, and I saw a very brief eye-like formation. I had deep convection, lots of ice water path, but no lightning. It was after the mature states. Some tropical cyclones have this drop of lightning activity during deep convection. I also have to investigate more lighting information, this type of convection, because of the slantwise ascent of air parcels there. Maybe there is a proof that it's correct. It depends on what you define as an eye, because a warm seclusion, a shallow warm air seclusion cyclone has an eye. Is it an eye?
That's why I will say an eye-like feature. I mean,
Okay.
not an eye, but a eye-like feature. No, which is the same as in the North Atlantic, the National Hurricane Center, where there is an eye, well, at certain stages as a tropical cyclone. They tend to call more an eye-like feature because they are not sure if this is because of subsidence or not. So that's why from satellite, if there will be a method from geostationary satellites to infer if this is an eye-like feature or an eye, I think it will be a good method to distinguish between for the dynamics of the cyclones. I mean, if convection is playing a role in the dynamics, or there are some mixing mechanisms playing a role.
We need to move on. One quick question and one quick answer. Otherwise, we won't have any food.
I'll be fast. You know, I think you raised an important point about the false alarm, because frequently you see this medicane that at the end does not occur in reality. So in that particular case, it was a problem related to the model, or was you see if other model predict the same, because they can say a lot about also the reliability of a model and probably the way to treat convection.
It was not dependent on this model because all the models were showing the same thing. This is why also the National Service of Italy issued this ban. I also see, like, because I'm also involved in operational forecasting, that we have more than 10 cases per year, only one or none is materialized. It's model dependent as well for the long-term forecast, but if it's in less than 48 hours or 24 hours, I think something is missing in the physics of what we have now in the model, or the assimilation of data they have, or the forcing they have. I don't know. I'm not sure.
Okay, thanks. We'll move to the next speaker.
Okay, well, you already read the title. This is basically what I'm going to present. 70% of this talk is based paper. It's all paper by Kerry and myself. But I would say the methods, the results are quite relevant still. But of course, as you can see, this downscaling is not properly a downscaling. It's kind of was based on the last generation models. So it should be updated with CMAP6 models, but I wouldn't expect so many changes. You can find the paper over there. Of course, the motivation is very clear. I'm not going to repeat risk that is imposed by these tropical like cyclones in the Mediterranean. And in that paper, we were concerned about frequency and also wind, but no rainfall. In the last part of the talk, I will present some more recent results where we apply a rainfall algorithm on those tracks, that on thousands of tracks we generated with this method to answer the question about rainfall. But for the moment, let's talk about this wind intensity, frequency, okay? So the method is based on the so-called statistical deterministic approach that was developed by Kerry for the tropics, for the ocean basins like Atlantic, which is a very clever method in the sense that you can, at low cost, generate thousands of tracks of storms, synthetic storms that are compatible with the climate, maybe for analysis or future scenario by the GCMs. For that reason, you can talk about probabilities in a robust method because you have many realizations to work with. But in the original approach, the genesis of these seeds was more or less random, or maybe following a known TF, which is quite known for the Atlantic basin, for instance, because there are many cases in the history. For the Mediterranean, that's not so practical. And then some synthetic winds were generated, but of course, I'm not going to details, but they respect the climatology. And these winds and the climatic properties, thermodynamic fields like potential intensity, etc., in the warm season in this. And these tracks were numerically simulated with an axisymmetric model, which is very fast to run. And from this, you can talk about what happens with these seeds if they progress real storms, and then to have some statistics. Many will fail, of course, won't produce for the Mediterranean, that was not the best method. We have to adapt the method. First of all, that was done in the tropics between fast scale, let's say winds, and environment, slow scale, is not appropriate for the Mediterranean, because we know that these storms, which are low frequency events, in very special circumstances that have to do with wave breaking, and this are not the scale weather system. We are dealing with fast scale and very specific conditions. So that's what this. In addition, we don't have a good PDF of Genesis because there are low frequency events. So what we did, and it's not so easy to explain in a minute, but basically we devised a method that synthetically generates cyanotic evolutions of the relevant fields that we need for this method, which is only geopotential at high levels, low levels, temperature in the mid-troposphere, relative humidity, and potential intensity. That was so important yesterday. So we basically submit 20 years of data from the GC for reanalysis to a exercise of principal analysis working on the spatial and interfield correlations, and then these species which are by definition uncorrelated are subject to another PC analysis through time. So basically, what we have is a method that by randomly choosing this collection of PCs, and we retain all information, all PCs, and any perturbation we want to introduce, we once converted back into physical space, we have, let's say, 10-day sequences of these fields that respect the climatologies. And we can thousands of times and submit this track to the intensity model and see what happens with these seeds. But of course, we even when genesis of a medicane is possible, because we want an efficient method. And that we use the Genitz parameter. This parameter that was formulated for the tropics condenses the basic ingredients like potential intensity, but also moist atmospheres. This is a positive ingredient. The presence of low-level vorticity is also a favor ingredient, but and shear, of course, is a negative parameter. This was work in this. This was developed or empirically adjusted for the tropical areas, but it's for the Mediterranean too. We observe when a medicane evolves in this area or this area, these are two examples, we have high values of this parameter. And we can focus the method on looking for an arbitrary value. We will units. When this occurs, we on the synthetic tracks, we will screen that for the intensification of this seed. This is, of course, many of these trials will fail, but so have enough statistics to draw some conclusions. Well, this has to do with the PCD selection. I will show an example of okay, so basically we have a method to produce synodic evolutions during 10. What we do is for these 10 days, if we observe in a C Genitz parameter above 10 units, we localize as a good possible environment for a medic at low levels. And with this, we track 12 hours backward and 12 hours maximum over land. And every 30 minutes, we have a description of this trajectory of this track. And this will be you run the CHIPS model and what happens, okay? Well, in addition, we have to decide how the storms, the cyclone moves. So we use a weighted average of working with the same levels. Necessary information in those 5-6 fields I showed in the previous slide. So this is an illustrative example for January 95 cyclone. Here we use this reanalysis. Again, all reanalysis, we will use MSEP and ERA interim in this paper. So this is the sequence, day 1, with these parameters. In particular, this is potential intensity. This is the Genitz parameter and the other fields I mentioned before. Third, and at some point, we have our criteria of enough Genitz parameter, and we build our tracks. And these tracks will be submitted to the CHIPS model, okay? This is real reanalysis, the MCIP. For the same period, we can illustrate how look like the analogs, the synthetic analogs. In this case, there are 2 possible tracks that we will run with the intensity model. And this is the storm. And this is the results with ERA interim. In this case, ERA interim doesn't detect, doesn't fulfill the criteria to run, to build and run a track. This is the previous result. And this is a synthetic analog of this one. There are different tracks that we will submit. And sit and car, another analog. This is more or less of the method. And let's go to results. So we apply the method to 2 reanalyses as reference, okay? Of course, we will run many tracks. We generate thousands of times. We have about 20,000 candidate tracks, and only some of them will survive and produce a medicane. This is winds above 34 knots, okay? And all results or the statistical results using the observed frequency of medicane. We apply 2 events per year, okay? And this is a summary of the track density based on both reanalyses. It's quite familiar with Western and Central Mediterranean are the most affected area, not so much the Eastern Mediterranean, but the reanalyses are different. This is number of tracks in 100 kilometers, okay, per century. And again, I repeat, by definition, these cases are retained, okay? And then we apply these to 30 models, 30 models from the CM5, okay? Well, these are the numbers. We always look for about 20,000 storms normalized. And this is the future. We use at the time this scenario, future scenario, and this is a small decrease of storms in the future based on results. So here we have numbers with lower storms than at present climate and more storms in red. So in summary, half of the models indicate reduction of medicanes, half of the models an increase of medicanes. But of course, not all models are equally valid. We observe, for instance, this is the track density, that those models are quite good compared with their analysis, but some other, for instance, these ones are not so good because they enhance this signal in the Eastern Mediterranean, which is not so realistic. So what we did was to decide and to retain only the 20 best model. So from now, I will talk about the best collection. This is the 20 best models, and I'm going to show the results based on these models. So for these models, again, half of the models show a decrease of medicanes, half of the models show a decrease by chance. But the decrease on the mean, on the average, is not so very substantial, 1%. So now changing so much. But let's see what happens about intensity of storms, okay? So here we check, this is the GCNs for the historical scenario. Well, these are the correlations of each, which is reanalysis, so of course is quite high, and the room is Romero, but consider these numbers. And this is the future. Of course, this change has to be evaluated by difference. This is the difference, future historical scenario. So we find more medicanes in the Western Mediterranean. This is the ensemble mean of the 20 models, okay? And in the Black Sea, and less cases, fewer area. And we also look at the consensus among models. So result, this means 2/3 of the model agree on the sign of change. And this one, double slash, means 80% of the models agree on the sign of change, okay? So we more or less assess the uncertainty of this average field, okay? Well, this is track density. This is for the Mediterranean, for the maximum lifetime wind, and what we find is in the future, from green to gray, is an enhancement of these very violent winds, okay? In addition, this is there is consensus among model in this sign of change. So more violent cases. Of course, these are very low frequency cases, but very catastrophic, no, in the sense. Okay, that's the result. We can check this in another plot, which is the return period for several whole Mediterranean, and it's very well. There are the individual models, but and the thick lines is the mean. We have the two reanalysis. Okay, we have the historical scenario. There is quite an agreement in this plot between, and this is the future. Okay, this is the future scenario, and of course we find lower return, so higher probability for let's say these violent thresholds, as you can see. In addition, there is quite an agreement, consensus, which is on these changes from right to left, from right to left for different thresholds. There is a high consensus. This is 80% consensus among models. Finally, about wind, we can explore spatial maps because this is an aggregate result. This is, of course, this is similar to the previous. Here we plot the return period for this threshold, which is a small one, and the changes future is very similar to the track density. But let's go with high consensus. So let's go to another very decent threshold, 6, for instance. we find here, when exploring the difference between two analyses, an increase of probability in the whole Mediterranean. So if we can more violent cases in the future according to the results, basically in the whole basin. And there is a very high consensus in general on this cycle. This is the old work. Now let's check the new results based on the rainfall algorithm. What has to devise a physically based rainfall estimation that can be used, apply on those tracks that we had from the 2017 work, and see what happens with rainfall across long storms and make our statistics. So, but first of all, if I have time, I think. I want to provide a context. I will choose two storms, two real cases, and we'll perform some numerical model simulation with my TRAM model. TRAM model is a model I built, which is quite a general model because it's non-isostatic, fully compressible, so you can predict many regional. You have interests here, and I choose two cases. I choose well, the model is open here twice daily. The predictions are updated on these three domains, different resolutions, different regions. Of course, this is centered in the Balearic Islands where I live, as you can easily understand. And first case, Thorbas, we simulate Thorbas on the big domain. This is the control simulation. So it's quite good. This is rainfall, this is wind. And I made the following test. I simply changed SST. This is to provide a context that in the future with warmer, what is expected, and you can guess the result. Well, first of all, I would say that these simulations are physically inconsistent because I keep the same atmospheres and I only change SST, but it's a first guess of what we expect. So this is the control simulation, and these are simulations cooling the Mediterranean or warming the Mediterranean, and we explore how the precipitation changes in the affected area, all points, ocean points, line points. This is the mean rainfall, but only taking points with 5 millimeters at least. And of course, we have this proven effect of SST on the accumulated precipitation. And this is a larger area, and again, the same result. As you could expect. And this is Daniel. Again, we have been talking about this case. Again, quite good simulation. This is when it is about to produce landfall in this area. This is the accumulated precipitation during this 4 days simulation. And this is a wind at the same time. And again, we explore the effect, the sensitivity to SST changes. And now we have this, well, it's more curious for very warm areas, but in this small, because of course, if you change the SST, the system, the dynamics also changes. So in this small domain, you find this result, but in the larger domain, there is this increase of precipitation. Well, that was only a break to provide context. Let's go back to the rainfall algorithm. I would suggest in this papers mention reference here, but this is explains quite well the hypothesis of this rainfall algorithm. The idea is that, well, the rainfall is formulated using a coupling of vertical velocity and saturation-specific humidity, and assuming some precipitation efficiency. But the key point is to calculate vertical velocity, because the CHIPS model is not very reliable about W. In addition, sometimes it's not recorded because it's very expensive. So we went back to the tracks and incorporated this rainfall algorithm that estimates vertical velocity with relevant physical processes, which are these 5 processes: topographic effect, boundary layer convergence, vorticity changes of the storm and the stretching effect, baroclinic interactions, the wind shear, and radiative cooling. So and you can read the method, the formulation of these contributions in the above paper. These are two examples for two particular synthetic tracks. This is one of the synthetic tracks in the Greek area, another in the Adriatic, and how the precipitation looks like based on this calculation. Okay, we submitted our thousands and thousands of tracks to this method. I summarize a few products. You can calculate the hourly intensity of rainfall, which is quite relevant, but here I will show the storm total rainfall. For two thresholds, 200 millimeters, what we expect based on these calculations. Well, this is again the result based on the first reanalysis, the second reanalysis. This is return period, okay? This is return period in semi-logarithmic scale here. We observe that the coastal topographic complex areas is the most affected area by rainfall. And here we have the historical GCMs, the 20 best models, okay? And this is the future. Okay, let's talk about the difference. And this difference is expressed in numbers. This is number of events per century, local events of this threshold. And we observe positive signal everywhere. So not only for violent winds we have probability in the future, but also very extreme precipitation. And there is uniform some models in this signal. We can explore another thresholds. For instance, 400 millimeters, and we have a similar result. Of course, this is less probable threshold, 400 millimeters, but again, if we explore the difference, we have a positive effect, a number of cases for these rainfalls associated to medicane-produced rainfall in the Mediterranean coast with consensus. And that was my last slide. I will conclusions. So basically, although this was applied to the previous generation when we have time, or maybe there are some volunteers to go that we can update that with the new models, maybe the future project, right? But of course, that's a good alternative to classical downscaling, which is very expensive. This is very cheap method. There is a lot of data, processing of data, but then since the software is done, is quite cheap to run. We find that total frequency of storms is not appreciably varying in the future, but there is spatial reorganizations. More medicanes in the Western Mediterranean and Black Sea, and a reduction in the Central Mediterranean, according to results. And talking about winds, it's very clear the result of a higher number of violent, moderate and violent medicanes at weaker storms, okay? For instance, for this threshold, the probability to look carefully more than doubles in the future, the risk, okay? And the last results regarding with rainfall on, again, a higher probability of very heavy amounts, 200, 400, even 800 millimeters, which of course are relevant in the topographic coast of the Mediterranean and associated with catastrophic floods sometimes. No? And for instance, again, we find that for these thresholds, the probability also doubles in many coastal areas according to these results. And that's all.
Thank you. Question?
I have two questions, if I might. The first is, did you say that in the best models, half showed an increase and half showed a decrease? Did you say that in the best CMIP?
In the best, yeah. Well, on the total number of medicanes, half of the models show an increase. So it's very uncertain. The mean, the average. Basically, there are no variation in the number if we attend to the mean. to the ensemble mean of the 20 or the 30 models.
That it then surprises me.
But more violent cases. Total number doesn't change, but the spectrum is changing. So we're more violent cases, both wind related or rainfall related.
What surprised me then is that you showed that 80% of the models agreed in the sign of the change in those patterns. And I don't understand how that could be if the models don't agree in the total particularly well. I don't know. Maybe that's a hard question. Let me ask a different. Let me ask.
Well, the consensus is in geographical point of view, and the numbers are the aggregate, but there are no big changes, so that's compatible. That's possible.
My other question may be a little more direct and answerable. In your precipitation analysis, were you able to look at whether the changes were constrained by Clausius Clapeyron, or were they super Clausius Clapeyron?
We
intensities
didn't explore. There are many in the original application of this technique to the tropical cyclones on the coast of the United States. They analyze which factor important. Of course, those coasts, for instance, topography is very shallow, and in those cases there are processes like low-level convergence, Ekman pumping, or vortex changes that are more important than topography. We could analyze because we have the information, but we didn't do that. Which mechanism is more relevant to vertical velocity and rainfall? I guess that topography here is very crucial in many areas. But more general question is, are these results compatible or follow the Clausius-Clapeyron hypothesis? We didn't explore that, but we could do that, of course. According to Paris' talk yesterday, globally, there are some constraints. Locally, this could work.
One last question.
It's just a curiosity. I was surprised when I saw this, not surprised, I saw the spread in the projection, as you said, the 10 models projected increase, 10 models projected decrease. Did you try to put these results in the context of the storyline, since you are using different GCM? I mean, power amplification, I don't know, tropical amplification, whatever. Just a curiosity, probably okay.
In the storyline
approach. I mean, you just classify the model in terms of possible forcing for these changes.
Oh, no.
Okay.
In fact, we didn't explore in detail why a particular model produced such signal or the other. Of course, this is much related with the basic ingredients I've shown.
Yeah, exactly.
Potential intensity.
Yeah.
Maybe there are more agreement with a large resolution. Some models at that time had problems. The Mediterranean is relatively small region, working with a GCM at, let's say, 100, 200, 300 kilometer resolution. Now the situation is much better, and I think they resolve much better the Mediterranean problems.
Okay.
Okay, so we'll stop here. So you can take it for lunch, box, and try to go fast to the restaurant, because we were told that there may be not much left after 12:45 or 12:50, so try to hurry up. So to find the restaurants, the best is to follow Stella. Okay. You have time to You can drop your laptop in your office and then go to her.